Okay, so what I'm going to do is I'm going to give you a PowerPoint that's going to hopefully help you with the last test here. You're going to have three or four problems that will be somewhat similar to what these problems are going to be. I'm going to go through them step by step, and hopefully you can repeat. You can apply this to the problems that you will have on the test, which I'll send out and next day or so, and that'll be it for the semester. Okay, so there's gonna be three problems. Uh, so you're gonna have these three guys right here. You're gonna have to figure out their bonding structures, and then you're gonna have to do some more things. So first of all, you're gonna have to find out the bonding structure of each one of these. Then you have to tell me what the shape of the molecule is and what its hybrid orbital is. So these two things are interrelated. Okay, so if you know the shape, you can figure out the hybrid and vice versa. And you can use the charts that I give you to figure these out. You can just look them on the internet. Also, you're gonna have to tell me if the molecule is polar or nonpolar or charged. Have to be careful about this. Okay. What we're gonna do is that each bond in the structure can be polar or nonpolar. Then, I mean, we can actually figure out the polarity, give it a quantitative number, use electronegativity. And also, what we're gonna do is find the formal charge on each atom in the structures. And then a couple of structures, this structure here, and this structure here, there'll be more than one possible structure. You're gonna have to figure out which one's best. And we'll just go over the types of bonds that you can find in a structure. And this should be sigma, not S, and this should be pi. Okay. First problem. All right, first problem is NO3 plus. One of the structures will be so there'll be at least two structures, okay, and I'll tell you that. So this should be TWO. Draw two structures, where one is a resonance structure. Okay, so we'll go over that. So first thing you need to do is count the number of valence of electrons that are available. Nitrogen has 5. Each oxygen has 6, and there's one electron missing. That's why it's plus charge. So you take one away. So 5 plus 18 is 23. Minus 1 is 22. So we can have 22 valence electrons, and when we're all done, we have to have 22 dots. Okay, we draw a skeletal structure right here. Now, instead of using the dot method where you pair dots and all that, what you do is you take the outer atom, which is oxygen, and you give it the number of lone pairs and bonds. Okay, and so just give oxygen 2 bonds, 2 lone pairs for all the way across. And so don't worry about it right now. It's not the right structure, but it's a starting structure. So what you do is you count number of dots. So we have 8, 8, 8. We can see that we have too many, and so we're gonna have to fix it. So we have 24. We're gonna fix it. Okay. So there's two problems with this structure. They have 24 dots. So we have to remove 2. So what 2 electrons are we going to move? Well, one of the problems that we're going to see is that nitrogen is a second row element, and it can only have 8 electrons. The way it has it in the previous example, it had 2, 4, 6, 8, 1, 2, 3, 4, 5, 6, 12, 12 electrons, okay? And it can't have that. Okay, each dash of 2. So why don't we just take care of? So we need to take away 2. So why don't we take the 2 away from the nitrogen? The oxygens are fine. Okay. So I'm going to take a bond off of here. All right. And oxygen can have less than 8 electrons as long as it doesn't have more. So right now, we're not quite done. All right. But we got 22. So we have 22 dots, but we're not fixed it yet because nitrogen still has 2, 4, 6, 8, 10. So what we need to do now is remove a dash. But you can't just get rid of it, all right? And this, like the last one, you just can't get rid of it because you still have to have 22 dots. So what you got to do is you got to move one of the dashes as a lone pair. And so what I did is I took one of these dashes right here and I moved it on the outside. So right like that. And now I have this structure here. Okay. Now nitrogen has 4 bonds, or 4 electrons, 8 electrons around it. And the total structure has 22 dots. Okay. Now this structure can actually resonate because this double bond can move to here and it can move to here, and so you can get 2 more structures. All right, and so what we can do is draw 3 of these, and they're actually considered just one structure. Okay, and so this is a resonance structure. So there can be 2 other structures, this guy plus these 2, where the double bond has moved around. All 3 all 3 are a resonance structure. Okay, so this is just one structure. Okay, now, all right, so let's just go over the types of bonds. Okay, anytime you have a single bond, it's going to be a sigma. Anytime you have a double bond, it's going to be a sigma and a pi. Okay, and we went over that in the lecture, and you won't have to know any more than that for this part. Okay, there could be another structure where you move the double bond, and one of the double bonds out as a lone pair, and so you get 2 oxygens with 3 lone pairs. So we have 2 structures that work. We have the first one, which is the resonance structure, and these ones. Okay, now let's look at the hybrid orbitals and shape for each molecule. Well, both molecules structures have 3 attachments. Okay, they have 3 attachments and no lone pairs on the center atom. So whenever you have that case, it's called a trigonal planar as a shape, and the hybrid is sp2. Okay. All right. This molecule is a charged molecule. That means it doesn't have a polarity. Okay, it has a positive charge on it. So the charge has plus. Oh no, so it doesn't have a plus or minus side because it's entirely positive charge. Okay. But what we can do is we can figure out the polarity of the bonds. And there's 3 nitrogen-oxygen bonds, so that's easy to find. So you have the electronegative oxygen as 3.5, and electronegative oxygen nitrogen is 3. Okay, they don't completely cancel out. You're left with the electrons being pulled in oxygen's direction, 0.5. So it'd be polar. Each bond would be polar towards oxygen, but that will not affect the overall polarity of the molecule, as it's a charged molecule. Right, next thing is find the formal charges each structure. So let's find for structure 1, which is a resonance structure. Okay, so it had 1 bond and 3 lone pairs on 1 oxygen, 2 bonds and 2 lone pairs on another oxygen. Oxygen with 4 bonds and 1 oxygen with 2 lone pairs and 1. So let's figure out the formal charge for each. So for the formal charge for this guy here, number of valence electrons minus the number of bonds minus the amount of dots. Okay, minus 1 is a formal charge for this oxygen. Okay, for the oxygen with 2 bonds lone pairs, it's 6 valence minus 2 bonds minus 4 dots equals 0. For nitrogen, it has valence at 5 minus 4 minus no lone pairs, so it has a plus 1. And the final oxygen had 1 bond and 2 lone pairs, so it's going to be 6 minus 1 minus 4 equals plus 5. Plus 1. Now, the sum of the formal charges is minus 1 plus 0 plus 1 plus 1 equals plus 1. And this is correct because the sum as of the formal charges has to equal the charge on the molecule, which was plus 1. Okay. Okay, structure number 2. Here it is right here. And it has 3 oxygens all with this, 2 of the oxygens with 3 lone pairs and one bond. Nitrogen with 3 bonds and an oxygen with two lone pairs and a bond right here. So what's the formal charge on each one? For the 3 lone pairs and 1 bond, it's 6 valence electrons minus 1 bond minus 6 dots equals minus 1, and there's 2 of them. Nitrogen has 5 valence minus 3 bonds minus no lone pairs and plus 2. Oxygen 6 minus 1 minus 4 is plus 1, and so that's its formal charge. Now the total formal charge, we have to check it. Minus 2 from the first 2, plus 2 for the second one. So this one is 2 times minus 1. The last one's plus 1. Add these up, these 2 guys cancel out, and you end up with plus 1, which is indeed the charge on the molecule. So which one of these 2 structures is the best? Okay, is it the resonance structure or this guy right here? So remember, so there's resonance, octet, formal charge are the things to judge it. So structure 1, this has resonance structure, and it had 3 octets. Each 3 of the so this nitrogen and 2 of the oxygens had octets. The formal charge, there was minus 1 on oxygen, a 0, plus 1 oxygen, a plus 1 on nitrogen. Now, just to let you know, so there's 4 formal charges here. Okay, that's not really great, but maybe the next structure will be better or worse. But the other thing is that you would like to have negative formal charge on the more electronegative atoms. And so at least this is a good thing here, even though, so this, one of the oxygens has a minus, the other one is plus. That's not a good thing. But the other good thing about it, it has a plus 1 on the nitrogen, okay? So these 2 are good here, all right? This one's not so good. And there's 4 of these, all right? So now let's look at the other structure, this one right here. It doesn't have a resonance structure. There's 2 octets right here and right here. And as far as formal charge, there's negative 1 on both oxygen. There's a positive 2 on one of the oxygen, and that's not good at all. That's this guy right here. And finally, there's plus 1 here, which is okay. So this guy right here is really not good because you don't like to have a positive on a high electronegative charge. So overall, this has, this guy up here, 3 formal charges. This one has 4. All right. So overall, the first structure is better because it has a resonance structure, it has 3 octets, and it has formal charge that seems to works for it better than the second one. Okay. So the first structure that we had is probably the structure that exists for this molecule. Okay, problem number 2, xenon hexafluoride. And all we're going to do is just get one structure. So we're going to count the number of valence electrons. Xenon has 8. Each fluorine has 7. So it's going to be 6 times 7, 42, plus 8 is 50. Okay, it's 50 valence electron. Draw the skeletal structure. Then give the outside atom the number of electrons, number of lone pairs and bonds as a second row element, which is fluorine anyways. So put that in and then count up the number of dots. So there's 8 electrons around each fluorine, so there's 48 dots. So we're missing 2 and a 2, so we need to put 2 more, and we're going to put them on the xenon in the middle. Okay, so there you go. There's the bonding structure. All right. So this molecule has 7 attachments. It has 6 bonds and 1 lone pair. So its hybrid is going to be sp3. So there's 1, 2, 3, 4. And then it has 3 of the D's. So you can write out S, P, 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 D, D, D. All right. And that's a hybrid. Now, you can look up the charts. Unfortunately, we don't have a shape that's a sp3, D3. So I'm not sure what that is. The highest that we go up through in our tables are sp3, D2. So if you get a problem like this, just say that. All right. So I don't know its shape, but I have the hybrid. Okay, this is a polar molecule, and the way I can tell it's a polar molecule is that one of the tricks is it has more than one thing attached to it. It has fluorines and lone pairs. Okay. As far as polarity of each bond, if you look up the electronegativity of xenon, it's not given. But one thing you kind of can assume here is that the reason why this molecule even exists is because fluorine is, like I told you in the lecture, the reason why these happens is the outside electron is trying to reach in and grab electrons off of the center atom, and therefore is higher electronegativity. So you can just kind of assume that fluorine probably is more polar, and electrons are probably moving from xenon to fluorine. Okay. Okay, as far as formal charge goes, there's only 2 formal charges. There's xenon. It has 8 valence electrons, 6 bonds, and 2 lone pairs. 0. Each fluorine has 7 valence electrons, 1 bond, and 6 dots. 0. Add these up. 0 plus 0 is 0. The charge on the molecule is 0. So that makes sense. All the bonds are single, and thus they're all sigmas. Okay. Last problem. SO2 2 minus. This might be called hypo. So SO4 2 minus is sulfate. SO3 2 minus is sulfite. This might be called hyposulfite. And so I don't worry about that. Just going back to what we were taught. So find the number of valence electrons. Sulfur 6 plus 2 oxygens is 12 plus a 2 charge 2. 6 plus 12 plus 2 is 20. So there has to be 20 valence electrons or 20 dots when we're all done. Skeletal structure. Okay, give oxygen, the outside atom, 2 bonds, 2 lone pairs. Count number of dots. You got 2, 4, 6, 8, 10, 12, 14, 16. We're 4 short, so put 2 sets of pairs on the sulfur, and we're done. And this is a possible structure. It doesn't. It obeys the octets. It's okay for oxygen is the second row. It can have 8 or less electrons. Sulfur can have expanded octet, so this is fine, and this one's fine. Okay, so this is a possibility. So we'll call it structure A. Can we come up with other structures? Okay, so now we can get other structures well by moving the pi bonds to lone pairs. So what we're going to do is take one of the lone pairs and move it out as a lone pair. And we can do that twice. So we can do it, to 2 sides. We can do it. We can take this guy and move it out here. So this is not supposed to be here. Or we could do it the other way. All right, so we have 2 of these guys, and this is just one structure. It's called a resonance structure. So we'll call this structure B. Right, we can get another structure where both double bonds come out as lone pairs, and then you can get this. So we have 3 structures, A, B, and C. Before we go on and try to figure out which one's the best, let's look at the shapes and the hybrids. All of them have all the shapes have 2 connections and 2 lone pairs. So they all have 4 attachments. Okay. Anytime you have 4 attachments, it's sp3 because it has 2 bonds. And what mean bonds is the connections, 2 connections, and 2 lone pairs. So this is a bent. All of these molecules are bent molecules. In terms of polarity, this is a charged molecule, so it doesn't have polarity. But the bond can be polar. And then there's only one type, and that's sulfur-oxygen bond. And here it is up here. Oxygen has a pull of 3.5, sulfur 2.5. So the resultant ends up being 2.5. 1 polarity towards oxygen. So electrons are being pulled towards oxygen for each bond, but that doesn't affect the overall charge, as the charge of this molecule is -2. Remember, you can have polar molecules, nonpolar molecules, and charged. If it's charged, it's given a charge. If it's not given a charge, it's either polar or nonpolar. Okay, so we're going to do find the formal charge of each structure. So here's structure A. So it has these 2 oxygens are the same in terms of formal charge, and then you have the sulfur. So the oxygen, there's 2 of these. Each one has a valence of 6. They have 2 bonds and 4 dots, so the total has a formal charge of 0. The sulfur has valence 6, 4 dashes, and 4 dots. So there's 6 minus 4 is -2. So this guy has -2, 0, 0. Okay. And when you add them, it's -2. Okay. Now, one thing that we're going to come back to is that when we use formal charge to help us find out the best structure, it's not usually good to put a negative charge on the least electronegative atom. So you can, even though this only has 1 formal charge, where it puts that formal charge is kind of a big deal. And when we look into figuring out these structures, we'll structure number 2. So it has sulfur with 1 bond and a double bond and 2 lone pairs. It has oxygen with 2 bonds and 2 lone pairs, and oxygen with 1 bond and 3 lone pairs. In terms of formal charge, so it's going to be 6, the valence of sulfur, -3 bonds, -4 dots, -1. So put a -1 right here. The one with 2 bonds, 2 lone pairs is going to be 6 -2 bonds, -4 dots is 0. So this guy gets 0. And sorry, that should be a 0 over here. And then the last one is 6 -1 bond -6 dots is -1. So that should be a -1 here. Okay, now this is better than the last structure because at least doesn't give all the negative to the sulfur. It gives one of the negatives to the oxygen. And this structure here has the same formal charge. Okay, structure C. Okay, structure C has 2 of these and 1 of these. So for 1 bond and 3 lone pairs, it's 6 -1 -6 dots equals -1. So each guy's on here gets -1. And our center one gets, center sulfur gets 6 -2 bonds, -4 is 0. Total formal charge is -1 plus 1 equals 0. That's right. Should be a +0 in here as well. Should be +0 equals 0. Okay, what structure is the best? So the first structure, there was no resonance structure. It had 2 octets, okay, both oxygens. the formal charges were 0, 0, and -2. And so, okay, so number 2 had resonance structure. 2 of the oxygens had octets. 2 of the structure atoms had octets. The formal charge went -1, 0, -1. I said that was better than this one up here. And the third structure, there was no resonance. It had 3 octets. And so this one had only 1 formal charge, but had a big formal charge. And it's a big deal. And the second one had 2 formal charges, but they're split up. And this has 2 formal charges split up as well. Okay, now if we look at these two here and compare the formal charges, this one is going to be better because it puts negative charges on the oxygen. So formal charge of all these guys is going to favor this guy. So formal charge is going to favor this one right here. All right. Now octet is going to also favor this structure here, but resonance is going to favor B. Okay. So so this is a kind of a toss-up between these two here. Resonance is a really powerful, really powerful thing to determine structure, but the fact that it has octet, an extra octet, and the charges are distributed kind of like how they should be, where the negative charges are on the most electronegative atom, suggests that it could be this structure here as well. So I'd be hard pressed, and I'd have to look it up to find out which one of these two structures are best. And I don't know which one it is, but so what I would like you to do if you get a problem like this is explain why each structure ranks like it does. So number 1 is the worst because it doesn't have resonance, has the lowest amount of it has only 2 octets, and it puts a negative charge on the most electropositive atom, the sulfur. Okay, no, and then it's between B and C. What makes B good is a resonance structure. What makes C good is the number of octets and how the negative charge is distributed. The negative charge is distributed on the electronegative atoms. All right, so that's how these problems are going to be that you're going to have on a test. Hopefully this helps you out. At least give it a go. And oh yeah, anytime you have a single bond is sigma, and anytime you have a double bond, it's going to be a sigma or a pi. And if you have a triple bond, it's going to be a sigma and 2 pi's. Okay, so hopefully this will help you out when you do the problems for the test.